Hey, I'm B. This is Luisa. So we're going to talk about how you can use abstractions to improve verification for hardware. It's not hardware specific, it's just the angle that we're going at this from. So first, we'll be talking about a lot about this. This is CIRCT. For those who aren't familiar, I'll give a quick sort of briefer of the deal with CIRCT. So if you're designing a piece of hardware, you have these low-level languages, System Verilog and VHDL. A lot of the time, you'll just write something in them. Sometimes you'll use a higher level language. Most of the time, to actually feed that to any tool, you go through System Verilog. And so you might use one of these languages to design a CPU. And you say, great, I think this is right, I'm not sure. So I'm going to simulate that. So you'll feed it to a compiler and an optimizer. And then that works. And you say, great, I want to put that on an FPGA. I'll turn it into a chip. And a lot of the time, you'll have a completely new compiler and optimizer to actually synthesize that into real hardware. Or you might say, actually, I'm not sure that I did that right. I want to do some formal verification. I want to do some logical equivalence checking or some formal verification with model checking. And again, you tend to see completely new tool chains for these, especially in open source. And I think it goes without saying that we don't want that. There's a load of tools you have to learn your way around. Nothing's really reused. Everything's re-implemented. There's a load of redundancy. If only there was some tool that we could use to make this better. So in CIRCT, we use MLIR for that. So we have the CIRCT core dialects. That's the register transfer level. So it's your gates and your registers. And everything sort of feeds through this central representation on its way to those backend tools, a lot of which we actually provide in ourselves. It's MLIR, so in practice it actually looks more like that. And we've got some import dialects and some export dialects in different representations. Technically it looks like that, but that's a bit horrible. So we stick with this for now. So I'll quickly run through sort of the standard verification flow in CIRCT. So we have this tool called CIRCT BMC, and it does RTL level model checking. So you have some registers and logic gates. You might have an AND gate, feed that into a register, and that gets converted into a load of SMT formulae. For anyone not familiar, an SMT solver basically receives a set of equations and it checks to see, is there a satisfying assignment that makes these equations hold? And so we convert this to a set of SMT formulae. And all of those MLIR values become SMT variables. And then you basically unroll it clock cycle by clock cycle. You say, in cycle 0, this is what represents the design. Is there anything that violates this property that I want to know holds on my design? And then hopefully the SMT solver goes, I can't find anything that breaks that property. And you go, great, what about clock cycle 1? Here's the new set of equations. What about clock cycle 2? And you keep going up and up to your bound. And hopefully you don't find anything that breaks the property that you're checking. And that's called unrolled bounded model checking. So in CIRCT, we've got CIRCT BMC that does that for you. There's a load of other tools too. So we've got a System Verilog backend, verifying System Verilog. There's loads of tools for that. There's eBMC, there's Symbiosis. We've also got a backend for this representation called BTOR2, and that's a really common hardware model checking representation. There's a front end for a load of tools, AVR, BetaMC, and UXMV. And that's great. You're really spoiled for choice if you want to verify hardware. The problem is if you've got some high-level dialect. So say that you've got this FSM dialect, which represents finite state machines, and that could come from high-level synthesis or come from our Python front end. And you can still go through that flow. The problem is that the FSM dialect has a load of really nice structure that's really helpful for verification. And when you do this lowering down to the core dialects, something's got to go in the bin. And in this case, what it is the structure. You're getting rid of that structure, and that structure is really valuable. So, I mean, this is kind of a hand-wavy intuitive example. But if we look at this FSM, x starts at 0. As we go from state A to B, we increment x. We go to state B to A, we decrement it. And we can see that sort of x is toggling between 0 and 1 there. It's never going to be more than 1. So if we have the state C and we say you only go into it if x is greater than 1, and we ask, can C be reached? It's pretty clear to us the answer is no, and I'm sure you can see that for a solver, there's sort of a pretty clear structure of how you'd solve a problem like that. If you have the RTL representation, which is a big messy circuit like this, suddenly it's a lot more complicated, it's a lot less clear to query, and I'm sure you guys agree, if I was given that, I need much longer and a pen and paper to figure out, can this ever be 2? So what we do is we say, okay, for the time being, we don't actually care about all of this RTL stuff that's going on further downstream. We're just going to generate our SMT models directly from the FSM. And that means that we can sort of maintain that structure in our model. We're doing this to dodge this lowering between the core dialects and going straight from FSM to SMT. Like I say, this isn't necessarily a hardware-specific thing. So this could equally be a lowering from SCF to LLVM or affine to LLVM. But like I say, we're doing it from FSM to SMT, and Luis is going to run through the model that we use for that.
Yeah, so we've seen how CIRCT contains some higher level dialects that allow us to represent different hardware abstractions. Now the question is, can we get some information that is useful verification-wise at that higher level? And in particular, is there some property that is useful and that we can check by looking at the FSM before the lowering, basically? So to answer this question, we introduce a lowering that basically converts FSMs into SMT models. So what we want to do with this lowering is to create an SMT model that describes the behavior of the finite state machine. And then on this model, we will check some properties. And these properties will guarantee us that the behavior of the FSM respects them. Now, before going into the lowering itself, let's take a look at the structure of the FSM dialect. So the FSM dialect has a very regular structures. There are some variables which exist within the FSM scope. There are some states. Each state can produce an output or more outputs and can have one or more transitions. And each transition can be activated by a guard that describes the condition for the transition's activation and can cause an action. So it can cause an update in the variables existing within the finite state machine scope. Now, let's consider an example, a transition that goes from state A to state B, and that is enabled when a condition described by guard G is satisfied and that causes an update in the variable described by action A. Now, when we want to describe the state of a finite state machine, we first of all need to introduce a model of time. So we need a discrete model of time to be able to say that at a certain time, a state is active or not active in that FSM. And similarly, we need to describe the input of the FSM receives at a certain time step. So overall, to fully describe the state of an FSM, we introduce a Boolean uninterpreted function that is a function of the variables and of time. And when this function returns true, we know that that state is active at that time. And when the function returns false, that state is not active. So we do the same for the arriving state of the transition, which will be reached at time t+1, and which will have another set of inputs that are function of time t+1. So we have another uninterpreted Boolean function, and now the question is, how do we connect them to represent the actual transition? So the way we connect them is by an implication. So what this big implication says is that if state A is active at time t, and the guard is satisfied at that time, this implies that at time t+1, state B, so the arriving state of the transition, will be active. Something important to consider when looking at this transition, at this implication, is that we first of all only consider uninterpreted Boolean functions, both for the description of the inputs and for the description of the states. And another important aspect is that the implication only bounds a necessary condition for the state's activation. And this is something that is very important to keep in mind when we are designing the properties that we want to check on this model. So speaking of properties, the first family of properties we want to check is liveness property. So we have converted our model, all of our transitions. We want to check that eventually a certain state will be reached in the traversal of the FSM, so that a state B is necessarily reached. How do we encode this? So we use, again, an implication. So we say for all time step and for all variable values, the function representing that state implies false. We can basically represent the implication as a disjunction and simplify this expression further, thus reaching to this expression. So for all times and for all variables, the function is always false. If the solver returns unsat for this property, it means that the state will be reached necessarily at some point of the traversal of this FSM. So if we consider an example, a simple finite state machine with an initial state as 0, and we want to check that under any circumstances we will always reach state Sn, we can basically traverse this FSM, and whenever we reach a state n and we are forced basically to reach it, the solver will return unsat, thus guaranteeing that Sn will be reached at some point of the execution. Now, moving on to safety properties, again, we would like to check that something holds for the entire traversal of the FSM. So, for example, that a certain variable always has a certain value in a certain state. So in this case, we also would like to represent this property as an implication. So saying that being in a certain state implies that a variable has a certain value. However, in this case, we expect a set result. And in particular, managing this kind of result is still a work in progress thing in our model, because we are still figuring out how to better express this property such that the SMT solver can digest them. Now, how do we test this whole infrastructure? We consider two main benchmarks. A first benchmark coming from the hardware speculation project, The Lord of the Rings, from HLS real FSMs. And then we construct a synthetic benchmark of linear FSMs to basically evaluate how our model scales. So first thing first, we convert our FSMs into SMT dialect, and we export them in SMT-lib format. We then check these SMT-lib formats using Z3, and we compare the performance of Z3 with CIRCT BMC. So we lower the finite state machines down to core dialects, and we basically use CIRCT BMC to check the same properties against these FSMs. So let's see how these results look like.
Cool. So these are fairly preliminary results, so take them with a grain of salt. But on the left, we've got our HLS FSMs. On the right, we've got the synthetic ones. Red line is 1x, and the green bar is a speed up. So it turns out that this structure is actually really valuable, and the SMT solver is able to sort of step through that in a way that is a lot more productive. It's worth saying that we're comparing this against bounded model checking in order to sort of not put bounded model checking at a disadvantage. We've given it a fairly low time bound. In practice, you'd probably want that to be higher. But yeah, basically, it's faster. The next question, how can you trust us? I mean, obviously, we've got very trustworthy faces, but we're saying that this SMT model and this core dialect model are equivalent. And that's a pretty big sort of leap of faith to take when you're verifying a piece of hardware. And so this current sort of work in progress way of verifying that is on-roll bounded translation validation. So the idea is fairly simple. We basically have this FSM model in SMT, and we have this core dialect representation. And we step through cycle by cycle, because the RTL bounded model checking is cycle by cycle. And in each cycle, we're going to get a value of X out of the FSM, and we're going to get a value of X out of the circuit. And we basically just ask the SMT solver, are these always equivalent? Is there any example where these outputs could differ? And then we step through and we check if that's the same for time 1 and for time 2. And again, you do this up to a bound to basically confirm that those two models are actually functionally equivalent, as you'd hope. Yeah, we're done quite early. But basically, the takeaway is MLIR's got a load of abstractions, and they're not always used. So we might as well make sure we're using them wherever we can. They can be quite useful. They can make things really fast. Thanks.
Thank you. Questions, please. Looks like everyone ready for the lunch.
I have one. Go. So you say that you check if both of them, if both the high level and the low level is equivalent in every state.
Uh-huh.
I assume you actually found that they are equivalent?
That's what we're expecting. Like I said, it's work in progress. So
Okay.
I'm skimming over the details. It's subject to change. But by the time this gets upstream, that's something that we're planning to have done so that it's sort of trustworthy.
Very cool. Thank you.
Thank you, Bea, Luisa.